I'm very disturbed by the fact that someone has the same MA/MD as me, Marie-Aline Martin Drumel. This is very disturbing. This is very disturbing. It's the first time in my life it happens. And it is in PCMI. This is very bizarre. Very bizarre. So Marie-Aline, I hope we meet.
Sorry about that.
Oh, no, I want to meet you. So, okay. Yeah. So let's talk about SKA now. So I will make the status of the project and some very general guidelines. I need to be where here. Okay. I need I'll do that. So I will just give you some the status of the project and some very general guidelines of what we are going to be able to do with these two telescopes. So SKA is in fact two telescopes, one in Australia, which is what we call SKA low, so the low frequency part of the observatory, and one in South Africa, which is SKA mid, which is the high frequency part that includes the 21 centimeter line and up to gigahertz frequencies. The numbers of antennas is very high, so it's 130,000 antennas in Australia. There's 200 dishes in South Africa, 15 meters dishes over 120 kilometer baseline. So that's what we call SKA1. So there's also an SKA2 project, which is the extension of those facilities to even more dishes and more antennas and larger baselines. In the dream of SKA2, the mid part has 2,000 dishes over 2,500 kilometers baseline. So, but that's for later. Now we are fully committed to build the SKA1 phase. So just to give you, these are important numbers to have, the timelines and the status of the project. So as you might know, in December last year, the French government had decided to join the SKA Observatory. And in May, the Council of SKAO, this SKA Observatory, has voted in favor of the entrance of France as a full member. And a couple of weeks after that, in July, they announced they approved the start of the construction. So we are in a phase where, we're starting to build SKA. And it will, it's happening now. And the current plan is to have in early 2024, enough station on both sides to have a demonstrator, what they call the area assembly 0.5. And that's the first step of the construction, where we would have enough stations in both sites and all the computing facilities that would be available and up and running to be able to have a demonstrator. Operation readiness is for 2027, and the end of construction is 2028. And so that's when the key science program would start. So that's the timeline of SKA. Yeah, Jérôme.
The demonstrator means it will be open to the community, or no?
No. At this point, it's just a phase of the project where you want to make sure that everything is working, the link between all the correlators, the computing facility, because it's really at a scale that has never been done before. So all this, so they want to have a demonstrator. I think that's the best way to put it. Yeah. So no, it's not going to be open for observation yet at this point. Okay. So I need to show those graphs because everybody do. So radio frequency people have the tendency to put things in frequency, and the mapping speed or the sensitivity, as you will see, it's like in a reverse scale. So for the mapping speed, it makes sense. So the mapping speed is extremely high. You will see for sensitivity, it's kind of strange. It's the next slide. So you see other current observatories, so LOFAR, GMRT, and JVLA and ALMA are on this graph over a wide range in frequency, as you can see. What the message you want to get out of that is that the mapping speed is almost 2 orders of magnitude faster with SKA1 for low and for mid compared to what we are able to do now. And this is one of the strongest points of this observatory. It's going to be extremely efficient at mapping very large areas.
Where is the NGVLA on this graph?
The NGVLA, I don't know where this is going to lie. No, I don't know. I guess it would be comparable to SKA in terms of mapping speed, yeah. Yeah, well, yeah, these are official plots from the project. Yeah, I should ask them to add them. So yeah, that's the strange graph where the sensitivity is the reverse way of what we're used to. So better sensitivity is up and worse sensitivity is down. And so here, the increase is smaller than for the mapping speed, but it's still almost an order of magnitude for SKA low compared to what we have on the ground. So combining this increase in sensitivity to mapping speed, you get a fantastic machine, and that's why the SKA is so exciting. In terms of beam size, so you see this is the kind of so this is at 1.4 gigahertz, so that's the 21 centimeter line of at Z of 0 for the galactic ISM. So the beam is going to be an arcsecond or a bit better for SKA1 mid, and for the low part, we would get a beam size of about 10 arcseconds at 140 megahertz. They are comparable to other experiments of the VLA and LOFAR, but the way they put it is it's noise with respect to natural noise. So it's kind of if you hit one here, you're perfectly at the noise level. So it's an interesting way of putting this. But that's why those experiments they lie on each other. So, but what you need to get out of that is the range of beam size that we will have. So it's arcsecond over sizes that are 100,000 square degrees. So that's the big seller for this type of radio observatories. So the science driver of SKA are not dominated by what we all love, the ISM. It's dominated by general relativity, the cosmic dawn. There's a lot of cosmology involved, galaxy evolution, but it is also entering the realm of the ISM with what they call the cradle of life, planet molecules, the cosmic magnetism, and they keep a box for the exploration of the unknown, which is always good to have in a project like that. So, but I'm not going to enter in this because this is not the topic. So I want to come to refocus on what we can do for ISM physics. What you will get out of my talk, I hope, is SKA will be able to trace the multi-phase ISM, and it's not a good machine to trace molecular phases, but it's a fantastic machine to do all the rest. And there's quite a lot to do on the rest of that. So the best asset of SKA is the atomic medium. So it's going to be able to make very precise, very sensitive, with fantastic spectral and spatial resolution of the 21 centimeter emission. So you will be able to use hydrogen recombination lines, radio recombination lines to estimate the density of the atomic hydrogen. You will be able to use SKA to do the study of the warm ionized medium using dispersion measures, free, and also carbon radio recombination lines. There will be some emission lines, and there are going to be talks after me on using molecular lines with SKA in specific conditions, especially with masers. OH is going to be fantastic with SKA, and for redshifted molecular lines, so it's also going to be a good tool for that. Obviously, we will detect continuum emission in the radio, so synchrotron is going to be a big deal to study magnetic fields and cosmic rays. We will be able to do Zeeman effects measurements with this instrument. And so rotation measure, grid, and Faraday tomography. So I would come back to this. And there's also going to be interstellar dust physics possible with SKA, with the highest frequency band, where we will detect thermal emission from bigger grains in disks, but also anomalous emission that it peaks around 30 gigahertz, so we will be able to detect this. So it's a very large range of physical processes, of physical probes of the ISM that is becoming possible. And why we want to do this? Well, I think if you look at a galaxy like that, this is a typical spiral galaxy. There's many, I could have taken many images like that. What is striking here is the size of the H1 disk compared to the rest of the where star formation occurs, and where we study it in detail using dust emission and molecular tracers. What we want to be able to do is to understand the evolution of matter in a general sense in galaxies. And this involves understanding how matter goes from the most diffuse phases to the denser ones. Because most of the mass in a galaxy like the Milky Way is in fact in the H1. It's not in molecular clouds by far. We have, so this is an image that is capturing the phase mixing of the, so this is not an artistic view, it's really based on observations, I can tell you. It's based on radio observation obtained with the Dominion Radio Astronomical Observatory in Penticton in Canada. And it's showing the link between free synchrotron and dust emission in star-forming regions. Each color is a different process. And so you see that those things are really mixed together, and radio is allowing you to see all those different phases and how they interact together. So I just want to say that, I mean, we all study the ISM from different perspectives. We all concentrate on some scales, physical process, density. We have all specialized into something different. And this is because studying the ISM is very complex. It's a very complex system, multi-physics, multi-scale, multi-phases. And but the challenge is really to put all that together. And why I'm interested in SKA, because it is providing things that we have not from other instruments. It's really providing information that we are not able to obtain from infrared spectroscopy or infrared imaging or molecular imaging, millimeter imaging as well. So I think it's a radio astronomy is really a complementary tool to what we do with other wavelengths. And when we talk about multi-wavelength analysis, I think this is really the art of it. And what's good is that we are living in a rebirth of the radio astronomy for now. So I'm talking SKA is going to be available for us in 2028. But what's good is that the community is building stuff right now, and we have interferometers that are working. So ASCAP is an interferometer that is a pathfinder to SKA that is working in Australia. And Meerkat is exactly on the site where SKA Mid will be built. In fact, Meerkat will be included into SKA Mid when everything will be built. It will just so extend the capability of SKA Mid that way. These two observatories are working, and with ASCAP, for instance, we are making very detailed studies of the small Magellan clouds at 21 centimeter right now. This is a paper in 2018 that was published, but we have much more data now, and we are working on this system. I will show an example later. And with Meerkat, there's this fantastic image of the galactic center that you might have seen. It is, if you want more details, you look at the Haywood et al. 2019 paper. They detect very fine, thin, elongated radio structures that are of unknown origin for now, and there's a big debate on the reason for these things to exist. You can see that on the image. These little filaments we see here, very, very thin ones that we don't really understand where they're coming from. So this is just giving a taste of what we will be able to do with those observatories. At the low frequency part, so what will be built in Australia, we have for now a LOFAR that is working. You all know that observatory, I'm sure. It's providing fantastic images for extragalactic physics, but it's also very useful to do galactic ISM physics. I will show an example later, but this is an image of Faraday tomography that can be done on high galactic latitude clouds, where we can study the link between the matter and the magnetic field in a very nice way. And I don't have an INUFAR result to show, but I'm showing a radio recombination line observation done with another SKA demonstrator called EDA, where they detect very strong radio recombination line from carbon and hydrogen in the galactic center region. And this is something we will be able to do with INUFAR. In fact, I know there are projects in INUFAR right now to do radio recombination lines observation of the galactic plane. Okay, so I've mentioned this already, the link between H1 and star formation, or the general evolution of matter in galaxies. This is going to be a very big topic of SKA. There will be surveys of nearby galaxies for sure, and we will be able to do parsec physics of the H1 in nearby galaxies and try to link that to what we observe with ALMA, with what we observe with NOEMA, and also with infrared and optical observations to really try to understand this link of how matter collapse and evolve into from the very diffuse gas down to the forming stars. So that's going to be a big topic for SKA. And one thing that is related to that is the way matters circulate in and out of galaxies, and how matter falls into galaxies. So it's not just the dynamics, the global dynamics of a galaxy, it's also its environment and the accretion. And we start to see this, these are velocity channels of the small Magellan clouds done with ASCAP. And you see those small colored clouds that are in the outside the galaxy that are, in fact, we are still debating if they are outflowing or falling onto the galaxy. But we are able to see that for the first time in the SMC. Those clouds are known in the Milky Way. We call them high velocity clouds. But now we are starting to see them and be able to characterize how that matter behaves in nearby galaxies. So that's an example of matter that is falling onto the Milky Way. And so if you can zoom on those clouds, this is the type of structure you would see. This is dust emission on the left, but on the right you have H1 observation of the same thing, where you have velocity information, so that the color you see there is related to different velocity channels, and you see velocity gradients, so you can really do the dynamics of what's happening when those clouds are falling into the Milky Way. So the H1 in the Milky Way is extremely complex, filamentary, structured at all scales. This movie is showing. Well, we're moving towards a piece of the galactic plane. It's data from Arecibo, from the GALPHA H1 survey. So you can look at Peak et al. 2018. So what you see here is, so it's moving in position, but it's also moving in velocity. So that's what you see here. There's a lot of structure. It's a very complex medium, but this is really the matrix out of which molecular clouds are formed, and that is what is, well, the complex MHD turbulence of that medium, and the phase transition that is happening here is really setting all the initial conditions for the formation of molecular clouds and the formation of stars. So understanding this very complex dynamical process is essential if we want to understand the whole evolution of matter in a galaxy. We cannot just concentrate, even though it's very exciting to concentrate on the formations of stars and planets. We need to understand the whole evolution process and matter spends most of its time in this phase in a galaxy like the Milky Way. So yeah. So this type of medium is multi-phase. We see that with narrow and wide lines in 21 centimeter. And now we have tools to do phase separation with the emission. So this is work I've done with my student Antoine Marchal last year, and where we used a code called ROSA to do a phase separation to separate what is cold and warm in the big region of the sky, and be able to do, in fact, physics of the H1. We use the same kind of tools. So these are again the Magellan clouds. This is a zoom on one of those, the hook that you see on the top, and you are really able to do the dynamics, so how the centroid velocity of that structure is changing over the sky, but also the velocity dispersion, how the line. So you have information about turbulence, about the thermal phase of the gas. This is something we do with molecular lines, but we can do as well with 21 centimeter quite efficiently. So SKA will allow to study the magnetic field. I mentioned that. So this is a Faraday tomography work that was done with LOFAR from Andrea Bracco, published last year, where they use the Faraday tomography. So it's the variation of the synchrotron emission as function of frequency to estimate the orientation of the magnetic field in the magneto-ionic medium. So it's the WIM, basically, at high galactic latitude. And the surprise was that we saw in fact a correlation between those structures you see in color in blue with structures in the CNM, so in the atomic gas. That was unexpected because Faraday tomography is really revealing the ionized gas, but now we're starting to see that there's a structure correlation with the atomic phase as well. And it's also correlated with the orientation of the magnetic field can deduce from dust polarization. So we are really starting to do MHD for the diffuse gas by combining H1, dust polarization, and Faraday tomography. So this is just a taste of what we're going to be able to do when we will have SKA, but it's possible right now. So I'll go fast on this. So there's going to be quite a lot of work on star-forming region on supernova, but that's quite a classical topic for radio astronomy. This is going to be fantastic for with the resolution we will have with SKA. And one topic that is maybe a bit less known is that we will be able to do dust in protoplanetary disk. I'm not joking. This is VLA observation of a Celto. So it's really possible to do that even with VLA. And we will, so this is just a model, a cartoon made by Leonardo Testi showing all the process of dust evolution in disks. We will have a resolution of about 4 or 5 AU in our star-forming regions. And so we will be able to study dust growth effect. So Anne and Maureen made a good talk about this earlier this week with ALMA. But so the idea is that with SKA we will go in at larger scales of dust grains with those observations. So it's complementary to ALMA. So I just want to finish by saying there's in fact a strong interest by the French community on SKA. This has been shown when we wrote the French SKA White Book in 2017. There's 11 chapters on different topics that was written by 40 scientists from 12 institutes in France on the nearby SM, turbulence, the formation of coal, atomic gas, molecular complexity, dust, Faraday tomography, magnetic field, jet outflows, supernova, the use of pulsar to probe the interstellar medium structure, and also distance determination, because when you have very precise measurements of, you can do parallax and radio as well, and do the equivalent of what you do with Gaia, with a radio telescope. So I would just conclude that there's a large range of diagnostic with high resolution, high sensitivity, high mapping speed that is opening a very different window to what we are used to. And I think personally, there's a very large range of ISM scientific topics to be addressed with these type of observations that are maybe different than the focus we have on star forming activity, on star forming regions, on molecular cloud. It's all the context and all the physics that is making that happen. So I think we have a strong ISM community in France to do this. There was a huge history of radio astronomy in France, in fact, and it's now becoming alive again. So I'll stop here. Thank you.
So there is a question by Quentin.
Salut Quentin.
Former student.
Yeah, well, yeah, kind of a postdoc.
Quentin, are you on? Okay, I will ask the questions. What is the policy for the SKA for the observation? Will it be open or what?
Yeah, so the policy is going to be the observing time will be mostly given to countries that are members of the SKO. So that's why it was so important for France to be in. It was important for France to be in to be part of the construction, so that there will be some contract with the industry in France, but it's also essential for us to have access to time. So it will be given to mostly to people that are PIs that are in countries that are members of the telescope. If you can apply for time if you're not a part of a member country, or you can also be on a proposal that is a PI, where the PI is from a country member country. And I have to also add that most of the time at the beginning for the first few years of the observatory will be given to key science projects. Only the PIs of key science projects can only be from country members.
So will there be some call for proposals for the large program?
Yeah, there will be so this is discussed right now, and so this is why it's so important that the definition of the key science program will be set in 2025. So there's still time, but this definition is happening now, and it's in the RS scientific working group organized in SKA. So people are organized in working groups. And the discussions are in the scientific working groups.
And the large programs will be defined for 5 years, 1 year?
That would depend. Yeah, no, I don't think there's a fixed time for that for each program. I don't think there's a fixed time. I mean, it's going to be a project. You say, I want to do this type of, it will take me that amount of telescope time, and it will be done. I mean, it will take the time it has to. So
because my question, this is a similar question by Quentin, is whether there will be one call and then it will be blocked for years, or whether there will be regular calls.
Okay, for the key science program, as far as I know, there's going to be only one call at the beginning.
Okay.
But SKA is going to last 50 years. So this is going to happen again, but for
you and me won't.
No, I know. I think we have the same age, though, but that's a different topic.
And also, do SKA plan to observe a large part of the sky that will be let's say available for the community? Like for instance, Planck mapped all the sky, and well, after sometimes it got public, and everyone could make statistics and stuff like this. I don't know if they plan to do the same with SKA.
I don't know exactly what's the delay between how long the data are proprietary. So I don't know that, but at some point, the data will become public. Yes.
So last question by Lionel Bouteiller. He cannot ask him because his microphone is not working. So he's asking whether what kind of data will be distributed. Will it be the raw data or the
Yeah.
reduced data, and if it's a reduced data, will the PI be able to upgrade the data edition if they want to get some specific?
Yeah. So this is a huge topic. The SKA is planning to be organized similarly to ALMA with regional centers. So there's going to be a European or French regional center. It's not all set. The difficulty is that the amount of data is much bigger than what we have for ALMA now. So it's a huge amount of data, and so the centers are probably going to be hosted by GenC or big data centers that on the same way that the CERN is organizing the data distribution. Yeah. So there will be, I mean, to answer Vianney's question, there will be several data products. And I mean, I just scratched the surface of what would be possible with SKA. There's going to be transient observations. There's going to be several different types of data products. Raw data, I don't think we will have access to raw data because it's just too big. There's going to be several steps of data processing at the position of the antennas in Australia and South Africa. And then the higher level product will be transferred to observing to member countries. Those regional centers will be able to produce higher and higher level of data products. So if we want to perform some specific analysis on the data, and that we cannot do it ourselves, it's a possibility for us to request that regional centers do such and such type of analysis. And this is all being defined now.
Okay, thank you, Marc-Antoine. We have to move on.